Now that we have the energy for a fixed n value for a state in the hydrogen atom, we can look at transitions, which is Bohr's third postulate. So if we go back, we'll see that we had delta E, the change in the initial minus the final energy states, and this looks a bit strange because we're used to final minus initial, but we'll see why the sign is flipped. And this is equal to the energy of the photon that's given out, where for photons, nu is equal to c over lambda. Okay, so we can just go ahead and plug in that this is now negative 13.6 eV multiplied by 1 over ni squared minus 1 over nf squared. Okay, if we want to compare this to the Balmer equation, we want a 1 over lambda, so we'll bring over the hc. We also want to get rid of the negative sign, so what we want is 13.6 eV over hc. So to get rid of the negative, then we swap around the next two terms. So this is 1 over nf squared minus 1 over ni squared. And we see that this is exactly the formula we had for Balmer's relation if this first term is equal to the Rydberg constant. And we'll show that it is by plugging in the values. So if we plug in that Hc is 1,240 nanometers times electron volts, which is just its constant value, then we'll plug that in here. Okay. The electron volts cancel, and if you now convert that into per meter, you do get the exact same value of 1.1 times 10 to the 7 per meter. So it does work out. And if we then remind ourselves of what this is interpreted as, we had on the bottom right, this is an energy level diagram where we start initially at what is called an excited state and then drop down to a final state energy. And in that transition, the lowest that we could go to is, for the Balmer series, it's still excited, it's still n equals 2. But if you have an n equals 1 state, then that is known as the ground state. All right, so that's the Bohr model. If we move on and we have Schrodinger's equation, then it makes sense to actually apply Schrodinger's equation to the hydrogen atom. And we looked previously at the time-independent Schrodinger equation, using that for a particle trapped in an infinite well, or also numerical ways that we can do this. And we could do this numerically, but actually here we can do this analytically, and I am not going to do that. We will save that for next year when you'll do that in quantum mechanics. But the first thing to point out is that the potential energy is still just that Coulomb potential, so that we have only a dependence on the distance of, say, the electron from the nucleus, so a radial dependence. And that simplifies things quite a bit because that gives you spherical symmetry. So if we want to write out the wave function, we do have to do this in 3 dimensions because an atom is 3-dimensional. And we are going to use spherical coordinates, where shown on the bottom left, we have this diagram for a point where it is a certain radial distance away, and if you sweep along in an azimuth angle, which is phi, then you can also go up an angle, the altitude or elevation angle, which is theta. So we have these three coordinates, and we can separate them out using separation of variables. So this is now going to be three functions multiplied together. One is only a function of r, one is only a function of theta, and one is only a function of phi. All right, that gives us then three boundary conditions for these three separate differential equations, r, f, and g. And if you focused first on that radial component, what you get when you solve for the allowed energies is exactly what you would get with the Bohr equation. So you get these quantized energy states of minus 13.6 eV times 1 over n squared. So that's pretty remarkable. Remember again that n is quantized, so 1, 2, 3. And this is known as the principal quantum number n. And in the Bohr model, there was only one type of quantum number, it was only n. But we'll see that's not the case here, because we also have the f and g differential equations, and we need boundary conditions for those. So if we carry on and we look at the f differential equation, which is a function of theta, then we see that this actually we can associate with a solution for the angular momentum, the orbital angular momentum. We'll show what that means. We could think about it roughly as that angular momentum we talked about in the Bohr model of an electron going in a circular orbit. We'll see that's not quite true, but it nearly is. So we'll think about it as the orbit of the electron. And this, we're giving the magnitude. So this is a reminder that angular momentum is a vector, but this is just the magnitude value. And what we see is an interesting relationship where we've now got a new quantum number, L. So we've got the square root of L times L plus 1, and that is all multiplied by h bar. So we have that L can take values starting at 0, 1, 2, 3, and so on, all the way up to n minus 1. And that's quite important, because if n is only equal to 2, then the most that L could equal is 1. So you can't have an infinite number of L. It's limited by what your n quantum number is. And then finally, we have our last differential equation, which was g, as a function of phi. And what we see is that if you solve the boundary condition, you get the z component of the angular momentum. And this has a pretty simple relationship where we've got another quantum number, ml, and that's multiplied by h bar. And ml, again, has a restricted amount of values that it can have, which are related to L. So we have that ml could be negative L, it could be negative L plus 1, it could keep going depending on what L is, what up to 0, and then it could go up to L minus 1, and then finally up to L. So it can be very simple. If L is equal to 1, then ML is either minus 1, 0,